So this is our last class. I figured that would be the best way to do it. I will post the exam sometime this afternoon, and then it'll be due Friday. So I figured that would give you guys enough time to work around whatever you guys have. I will be available Wednesday if you have any questions. I don't think it's necessary to have an official class, but we definitely can if you want. So let me make that clear, for especially for those who aren't watching this right now. What in the world letter is that? So I'm available all week, especially Wednesday. If you have any questions. So the exam will be due. That reminds me, it'll be due Friday at 11:59. Now, of course, if there's something, if you have a logistical issue where that's becoming difficult, that's fine. Reach out to me. I mean, that's not a problem. But you should have plenty of time to do it again. Let me repeat this. I guess I didn't write it down. So I'll post the final. Today. And then you'll have, I don't know how long it'll take you. It's going to depend on how sort of prepared you are, I guess, but I'm going to give you plenty of time. And there's going to be a writing portion to it. And I don't mean like writing, like you're not writing a 5-page paper, but there's going to be a portion of it where you're going to have to do a little bit of writing. Hopefully you can type it. So that might take a little more time, but I don't think it's going to be a difficult test. I don't know. And the other thing I would encourage you to do, did I update? I guess your grade. No, I didn't. Man, you guys should have, fired me already. So I did not update your grade. So what I'll do is I'll do that. And if you want to talk about your grade or where you are in this class, feel free to reach out. I mean, I'm not really, unless I reach out to you, it's not like you're in lieu of flunking anything. In fact, everybody should be getting a good grade. Everybody should have an A, a B at worst if you're doing the work. Hopefully everybody gets an A. That's the goal. But I can't give you an A. You have to sort of earn an A. That's how it works. Do the work. So please, if you're concerned about a grade or anything, just reach out. I'd be happy to talk about anything. And it's going to be difficult for you to do that until I actually update the grade book. So once I update it, then go from there. And if you can't wait for me to update it for everybody, then just shoot me an email and I'll get right on yours. So there we are with that. Okay, does anybody have any questions about, why is my voice cracking? What the hell is happening? Anybody have any questions regarding the exam or the course, logistics and final and all that, grades? Again, it's very unfortunate that we're doing things the way we are, and part of it is the unfortunateness of the timing, but it's also, this all happened so quickly, so it's not like we could, or I shouldn't say me, couldn't create the virtual sort of learning environment that I think would be better, but we did the best we could on short time. So I hope you guys understand that and don't hate me too much. All right, look, let's get into it. There's a few more things I want to talk about. We have to sort of, last class was, I was going back and thinking about it, and I don't know if maybe it seemed like things were disjointed or they seemed overwhelming. And I know the math portion of what we're going to do is going to seem overwhelming. So we sort of have to go back and pick apart why these things are connected and why they're important. So let's sort of form it, come at it from a different angle. So So last class, it ended with a short discussion, not short discussion, a short intro about exponential, what we call models. And why are they important, and how are they connected to what we're doing here? And that's sort of what we want to make sure you understand, that there's sort of like there is a connection. It's not just us just throwing different things. So let's look at that. So these are equations, or if you want to think about them, functions. And again, I don't want, don't get all tied up in the math jargon. So these are equations that have a wide variety of applications. Now, I mean, they show up in a whole mess of different parts of us as humans trying to understand the world. But let's just list a few that are sort of connected to what we've talked about in this class. And these things are typically studied in depth in advanced courses. Now, who knows if you'll even get into any of them, but that's neither here nor there. Once, like I've said before, this is an introductory physics course. It's a survey course. We're trying to give you a general idea of some of the physics that could be of use to you guys as, students in a program, in particularly in anesthesia and nursing. And, we can't go into extreme depth of many of these things, nor do you guys probably want to, but we do need to give you sort of like an overview and a glimpse into it. Anyhow, if we list these, just a couple, and then we can sort of dig into the big one that motivated this whole thing, and actuality. So here are some applications include, but aren't limited to, things like finance, chemical reactions, electrostatics. So that's the study of electricity. We gave you a tiny brief thing with electrostatics when we talked about charged particles and Coulomb's law. One of the things we've been talking about is this idea of heat transfer. And what actually ultimately led us to this equation on Wednesday was this idea of radioactivity, which we're going to sort of, we use that as a motivation to introduce this term, and that's sort of where we're going to go with a little bit today. So basically what we're saying, and if you have a question, please.
I mean, every class he says he's going to.
Hello? Oh, I thought someone had a question. So the big picture here is this equation, or not this equation, these sort of important topics and many others can oftentimes be explained or predicted, or I guess the more general term that we use in physics and mathematics is model some phenomenon. What they can usually be modeling is something like this. So let's pick, maybe we'll go to more traditional letters. Y equals some number we'll call C, and then E to the negative KT. So this is a very frightening thing, as we saw since homework 1. In the very first homework, I gave you a problem with things that looked like this, and we had a discussion, and who knows if that discussion was helpful or more hurtful. It could have been more hurtful, I'm not exactly sure. But nonetheless, you know, if we want to sort of get into how scientists study these certain things, it turns out that this equation is very important. And just a few things about this equation. It's a generic, abstract, mathematical thing right now. But we do make some things a little more clear. So, for example, C is some constant, which means it's a number. Typically, it has a name. We typically call it an initial value. We'll see what that really means when we do an application. K is typically also a constant. It's typically, but it's not just any old constant. It's typically a positive number. And then T is what we call the variable. So it, you know, we use T for time. So one of the things that, look, if you want to learn this, and I know I mentioned this the very first, I want to say, well, probably the second class, I guess, because when we talked about the first homework assignment, the big thing for trying to learn this and understand this is, can you get over the initial sort of uncomfortableness of looking at the ugly math? Again, some of you might not have that problem. Some of you might say, okay, this is just symbols. I'm okay with math. But what we find when we teach not just this class, but when we have students who encounter these equations for the first time, no matter what class it's in, that there is a large portion of students who struggle with this, and because it's hard to get over the hurdle of it's like a new language, and it's symbols that you're just unfamiliar with. And that's okay. But again, if you want to learn it, you have to get over that sort of what we call, I don't know, I want to say a fear, because it's not a fear, inexperience, or, you know, you just don't have enough exposure to these kinds of symbols to not be overwhelmed when they pop up. So anyhow, my sort of advice would be for you to think about what I'm saying when you're trying to learn this stuff. But you know, and then hopefully you'll go through it. Okay, so enough of the scary symbols for a second. Let's connect it with sort of what led us to it on Wednesday, which was this idea of radioactivity. So does anybody have a question or a comment? Okay, so spelling is very, very terrible. All right, so what are we caring about right now? What application do we sort of want to have in our back of our minds as why we're interested in these scary math formulas? And that's going to be what's called radioactivity. So as we've done numerous times, let's think about these complicated terms in as sort of a simple context as we can. So what is a definition, or what is radioactivity? So a good way to think about it is as follows. You have, we have these sort of, you have a nucleus, for example, and you say this nucleus has some certain level of energy. And if we think about sort of some of the things we touched on weeks ago about how energy is never created, it's never destroyed, it's just transferred from one thing to the next, if you will, if we try to say it in as simple as possible. And what happens is sometimes you have a nucleus that has a certain level of energy, and all of a sudden it doesn't want to have that level of energy for whatever reason. And we call this stuff radioactive decay, where it turns out the nucleus says, okay, I'm at this level of energy, and I want to go to this level of energy. In particular, it drops from high energy to low energy. So that energy has to be transferred elsewhere. And so when that happens, what we call this radioactive decay. The energy level drops. And so what we do is if we study how this drops, and we can record data, and we look at sort of what happens in an experiment, maybe it's in a laboratory, and we study how this sort of energy goes. What we notice is that there's a pattern. And so this pattern, when we do enough experiments, gives us enough confidence that if there is a formula out there whose sort of relationship, when we graph it, so if you go back to your early days in math class, and you have two quantities that in typical math class you called 1x and 1y, and they were related by some formula, you can graph that relationship. Some were lines, others were curves. You will probably remember things like parabolas, and maybe the word polynomial. So at some point in your life, you spent time learning how to graph, at least in school. I don't know if you did it for fun on your own, but you spend time learning how to visualize the relationship between variables mathematically. And we even talked about that briefly on Wednesday with these sine functions, these waves. And so what we're looking for is we're looking for some function whose graph, whose geometric visualization of these variables matches the data. And it turns out that if we go back one page, this is the creature that gets the job done for many things. Many things in nature behave very much like the curve or the graph of this equation. Okay, so if we come back to this, and we'll pause. Does anybody have a comment or a question? You don't even, maybe you're all sleeping. That's probably what I would be doing. I'd be sleeping right now. All right, so let's state what we want. So this is so the best, again, the best way, this is how I'm telling you to think about it. I'm sure if you went to your textbook, they might define it differently. I mean, I shouldn't say differently, but using similar verbiage. Google, you go to Wikipedia, you're going to find a very similar thing. But what I'm trying to do is define this in the simplest way, I think, for you to learn it, usually the way that it was for me when I learned it. So this is the process in which a nucleus loses energy by radiation. And you'll recall from last class on Wednesday, what was radiation? Well, radiation is one of the ways that heat is transferred, and it's the very special way it's transferred when you have these electromagnetic waves. So, and even more interesting, if you trace it a step further back, it ties into our previous stuff with electricity, because what is an electromagnetic wave? Is what happens when a charged particle accelerates. So you have a particle, it's charged, it accelerates, it creates this thing that we call an electromagnetic wave. Now, anytime these waves transfer or heat is transferred through them, we have a process, or what happens is we call it radiation. And now we're stepping it up a step further, where we're saying, okay, anytime we have a nucleus that's at a certain energy level and it spontaneously lowers its energy through radiation, we call this radioactive decay. And so anytime we observe something, we want to quantify it. Well, not maybe you guys, but scientists do, physicists do. And one of the ways that we quantify it is through these exponential formulas. So a couple things that we could also say about this, and maybe we'll leave the details of this to something you can write up for the exam, or learn on your own for, well, maybe fun's not the right way. So there are 3 common ways this happens. And so it might be a good idea for you to read up on it. The book talks on it briefly, but you can get more details without much work on the internet. So the first one is what we call alpha decay. And then beta decay. And then the third one is typically called gamma decay. These things are also, the ease at which it is to understand these is also usually dependent on how well you understand the basics of atomic structure and some things you learn in chemistry. And so, again, I encourage you to read about it. We're not going to go into the details about it, but it's certainly something that if you were curious about, you could have a deeper understanding without much work. So I would encourage you, if you're interested, and maybe you're not, I don't know, to do so. Okay, so let's get a different color. So let's pretend we're physicists. So we want to study and quantify and so one way to do this is to study what we call half-life. So I would guess, and I don't know if I should assume these things. It's never good to assume. But I would guess that you at some point you guys encountered this term, whether it was in a math class or a biology or a chemistry course. It's it's something we're going to talk about right now, just because it's easily accessible from the math standpoint, but it's also one of the most common tools for sort of measuring and quantifying what happens to these atoms in these nucleuses, or the nuclei, as we should say. So here's what we're going to do. Assume we have some quantity. It doesn't even have to be a specific thing. So let's assume we start with some quantity of something. I don't care what it is. You know, obviously it could be, if we're keeping along what we've been doing, it could be the energy of a certain nucleus, or it might be the number of atoms, or excuse me, the number of cells in a tumor, for example, that might be going under radiation treatment. We might be talking about the amount of money you owe on a debt, say a student loan or a mortgage. We have some initial amount of something. Maybe it's the number of certain type of fish in a specific lake. I don't know. All right, but we have something. So let's call it and we'll use traditional math physics language. We'll call it A sub 0. And so if you want the fancy thing, this reads A naught. That's sort of how we read that. And so what the zero represents is, the zero represents that some initial quantity. And why do we use 0 instead of like the letter I for initial quantity? Well, think of it as when we start our experiment or our observation, we are going to put our clock at 0. Our timer's at 0. And so once we hit that clock, time is now moving on. And then the obvious question we might, and I shouldn't say it's an obvious question, because maybe you're like, what is he talking about? In fact, you probably say that about me all the time. The question that we might ask is, okay, after say 1 minute or 10 minutes or 5 days or 6 years, whatever our time units that we're interested in, we might ask, how much is left of our something? How much is left on your mortgage? How much are you paying? How many cells are left in the tumor after 6 radiation treatments? I mean, again, I can keep naming countless examples, and hopefully you're starting to get the pattern here. So what we want to know is if if the quantity will decay exponentially, the amount left after some time t is given by, so let's write this down. So now we're going to write the letter A, and it's going to be equal to A naught e to the negative kt. So again, let's remind you of what these things mean. This is our initial amount. And this tells us amount at time t. Now, if t is in seconds, then this is in seconds. If t is in hours or days, then the unit is all given, you have to use your context clues. What time frame are we dealing with? Are we dealing with milliseconds? Are we dealing with hours? Are we dealing with months? Are we dealing with years? The point is, t can represent any unit of time. So half-life asks the question, how long does it take for us to go from A sub 0, A naught? How long does it take to go from our initial amount to half of that? So the half-life is the time it takes to go from A sub 0 to A sub 0 over 2. So if we started at 50 of whatever, how long does it take until we're down to 25? Or if we start at 1,000, how long does it take till we're down to 500? So as you would imagine, this is going to be completely dependent on one thing. It's going to depend on that letter K. How big is that K? How small is that K? That rate constant. Just like when you take out a loan, the amount of time it's going to take for you to pay off half of that loan will depend on the rate that you get. For example, your interest rate. And so what's fascinating about this is we see different physical problems, and we see that when we do these sort of experiments, they have their own patterns, but we see that there's a bigger underlying pattern, this exponential business. And so what's really good is it turns out that we can kill all these birds with one stone just by looking at this particular equation. Because with a little algebra, this equation is going to give to us the exact half-life. And as expected, and of course you might say, I don't expect any of this, I'm completely lost. And that's fine too, but if you were doing actual experiments, what you would expect is you would expect that this half-life depends on only one thing. And that is, it depends on that letter, which is which is really a number. The half-life is going to depend only on this constant K. So let's see why. So So why does it only depend on K? So let's think of this. So we want to know, so if we take this English sentence right here that I'm starring. So the half-life is the amount of time it takes for us to go from our initial quantity to half of that. So if we rephrase that sentence, instead of in an English sentence, if we write it in a mathematical sentence. So the starred sentence above translated into math is we want to know when is a sub 0 over 2 equal to a sub 0 e to the negative k t. So this is the mathematical equation that is equivalent to the blue sentence that I have a star by. So a couple things to keep in mind. And I know sometimes it's, again, our lack of experience, and especially with these letters and all this very abstract looking stuff, keep in mind that if you slow down and you remind yourself of what's happening here, a sub 0 is in general a number. Maybe it's 100, maybe it's 67. K is a number. E is a number. It's this number we mentioned way back on homework 1, 2.718, blah, 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 blah. So if you remind yourself of that, and you sort of keep reminding yourself that also T is the only variable. T is the only unknown. So if we want to figure out the half-life, that means we have to figure out which value we can plug into T to make this true. So what we're going to do is we're going to replace K and A sub naught with an actual number. And then we'll see how the math works, and then we can do it in a general case. So let's look at two examples. And I'm going to choose here a sub 0 to be 50. And I'm going to just, these aren't really necessarily realistic numbers, but I want you to see how the math works. And so let's just say now K is 10. So if I plug that in, you have 50 over 2 is equal to 50 e to the negative 10t. Now let's go slow here. And I haven't written this symbol in a while, so let's, this little sort of arrow with two directions, this is a mathematical symbol that's used when we're doing mathematical arguments. And the way you can read this is you can just read this as equivalent to. So this double blue arrow, what this means is that expression is equivalent to this. Because 25 is what happens when you take 50 and divide by 2. Now, if I'm going too slow with the math, that's okay. This guy is equivalent. You know, it's been a while, and it's almost been, you know, for sure you probably haven't touched one of these since we had it way back on homework 1. But I want to solve this equation. So my goal, let's, you know, this is probably not obvious for most of you. So let's remember what our goal is. Our goal is solve for T to get half-life. So how do I solve for T? Well, if we go back to I want to say our first or second meeting, we talked about this. You need to isolate that exponential thing. So the way I'm going to isolate it is I'm just going to play these baby algebra, sort of, not even algebra, these baby rules that you learned most likely in 7th or 8th grade, that if you have something on one side of the equation and you want to get it to the other side, well, there's two ways to do it. You can either add or subtract it, or you can multiply or divide, depending on what the context is. And the context here is I want to isolate this exponential. And so what I'm going to do is divide both sides by 50. So I have 25 over 50, which is 1/2. And so that's exciting because we expect this 1/2 to pop up. And it does. And then how do we get the t sort of? So if, again, the trick, or the, not trick, that's a bad way of saying it, the logically correct way of isolating this t, that's how we solve an equation, is we undo everything that's happening to t. So that's what we're slowly doing. So how do we undo this e, this exponential thing? Well, you might remember that that is undone by taking the log of both sides. So if I take the natural logarithm of both sides, that gets rid of the e. And so the only thing that remains now is for me to divide both sides by -10. And when I do this, I get t equals log of 1/2 over -10. So we're going to leave it like that for a second, and then we're going to make this look a little cleaner. Before we go to the next page, for those of you alive and paying attention, joining the party, does anybody have a question about this? For those of you sleeping, shame on you. Or maybe you're not even there. So this is a very ugly thing right now. Look at this. It's a log of 1/2. But we're going to make it look pretty in a second. Any questions, comments? Okay, so this looks sort of, there doesn't seem to be much of a pattern, or at least maybe not yet. An interesting thing to think about, though, is if I were to replace 50 with that a sub 0, and I replaced k, or excuse me, 10 with k, the same strategy would be used to solve this. So what we want to do, though, is, before we look for that pattern, is we want to write this a little more neat. So let's clean up, if you will. The equation above. So way back in some math class years ago, when you first learned about exponents, you would say, okay, here's what an exponent means. Here's what 2 squared means. Here's what 2 cubed means. Here's what 2 to the 4th means, etc. And then you would also have learned the inverse properties. So the logarithm is this inverse of the exponential. And the log has very similar properties too. And one of them is that, I'll put it over here. And you can verify this stuff on your own if you wanted to go play on a calculator for a little bit. But one of the more important log properties there are is this pretty fascinating thing. That is the log of some number a divided by the log of b is just equal to the log of a minus the log of b. So many, I don't know how long ago it was, but at some point, if you went to high school, at least in the United States, you sat in a class where they taught you this. Maybe it was briefly for 30 minutes and you never paid attention to it, and that's fine. Point is, this is a very common property of the logarithm. And so if we apply it to our log of 1/2, that becomes the log of 1 minus the log of 2. And the log of 1 turns out to be equal to 0. So this is equal to 0 minus the log of 2. Okay, so if we go back to the previous page and we write down what we had t, this was our half-life, was the log of 1/2 over minus 10. And so we saw that the log of 1/2 is just minus log 2 over minus 10. And of course, a negative number divided by a positive, a negative by a negative, we know is a positive number. And another way to think about that is minus 1 divided by minus 1 is positive 1. So this simplifies to just log 2 over 10. Does anybody have a question about this? So an observation to make is that in this computation, only 2 things survive. First that survives is the number 2, and then the number 10, which happened to be our k. Now that could be a coincidence. It doesn't have to be. And so one of the things that I don't want to say makes math people, but one of the bigger ideas or bigger themes in mathematics, for example, is to recognize patterns so that we don't have to continually do the same computations over and over and over again. And so if we suffer through 2 of those right now, and suppose we do it again, for example, let's just change the numbers, and then we'll summarize this real quickly. So if we repeat with this time, let's say a naught equals 150, and now let's say k equals 5. I'm just changing the numbers. So once again, we would start with a naught over 2. We want to know when that's equal to a naught e to the negative kt. And if we plug in these corresponding fixed numbers, 150 over 2 is 75. And then this is 150. And then if you divide both sides, you get 1/2 equals e to the negative 5t. And then if you take the logs, I mean, it's almost the same exact thing that we did last problem. And so if we summarize this, once again, you get t equals log of 1/2 over negative 5. But we know that that can be written as negative log 2 over negative 5, which simplifies to log 2 over 5. And so just like in the previous computation, log 2 pops up. The only difference in this computation, when you compare it to the last one, is the denominator. In the previous one, it was 10. In this one, it's 5. And so again, we start to realize that this shouldn't be a coincidence. And then if we are confident it's not a coincidence, the only thing is to verify it's not a coincidence. So let me put this in English, and then we'll do it in math again. So here is the conjecture. So it looks like this. The pattern is the half-life, which is the time it takes to go from half of your initial amount. The half-life is equal to log of 2 over k. We saw that to be true in 2 examples. And in fact, it's not even a big leap to get it to be true in general, because we could just repeat the previous 2 calculations with the letters A and K in there, and we'd get the same thing. So this is in fact true. And I'm not going to put you through another calculation, but you could do it on your own. And we denote this number by T with the subscript creatively 1/2. So the half-life, by definition, is always log 2 over the decay rate, which is K. So let me just say one more thing about this. If I go back to both of these calculations, the one here, if I just replace 50 with A naught and 10 with K, I'm going to get log of 2 over K. And if I went and did the same thing here, if I replaced, another way of thinking about that is if you look at this first equation right here that I'm circling, if you just started with that and ignored plugging in 150 and 5, if you just divided both sides by A naught, and then you did the same logical rearrangements, the quote unquote algebra, you would arrive at this particular expression for the half-life. So does anybody have a question about this? And what's great about this is we have most of this documented. Like if you have certain things you want to know the half-life is, you can Google it. Half-life of, plutonium is blah. Half-life of uranium is blah. Half-life of a certain medicine, blah. If I'm studying a drug, for example, I mean, if I'm going to put some drug into a patient's body, well, one of the things I might like to know is how long is it going to take for the medicine to be completely out of the bloodstream, or how long is it going to take for half the medicine to be out of the bloodstream? How does that change from an adult patient to a child? If you go back, it's not the same thing, but these are the kinds of sort of, I don't know what's the most effective way for you guys to gain something from this course, right? I mean, I think I've mentioned this to you a few times. Oftentimes what we do as students is we just go through the motions and go through courses because that's the way we do it. And oftentimes we might not think that we've gained anything. We might think it's a waste of our time. I don't know. Hopefully you guys will do those evaluations and let me know what was wasteful and what wasn't. Hopefully you'll be honest. I won't be mad. But if you want to gain things from stuff, what I would encourage you to do is think about questions I ask. So I always put this question. I think I put it on your first exam. I want to say it's the first one. where I said if you have a sphere or a cylinder and you take the radius and halve it, what properties does that have, and why are they important? And you might say, well, what do I gain from that question? It seems like a stupid math question. Uh, well, I don't know. There's certain things. I mean, you can phrase it in a context that might be useful to you. For example, if you're studying breathing issues or medicines or whatever it might be, for say how an adult handles a certain breathing apparatus versus a child, and you might say, okay, well the breathing, the parts of the body that allow a child to breathe, well, the sort of geometric size of them could be very much how that apparatus might work would be very much related to, well, how does it work on an adult when the radius of the mathematically simplified cylinder is cut in half? How does that affect things? So what I would encourage you to do, and maybe that was a bad example, I don't know, but what I would encourage you to do is look for context in all this stuff that might be important for you in your particular, what are you trying to gain? And of course, you might just say, well, I'm just trying to gain a sheet of paper so that I can get a better job and make more money. And that's completely cool. I get that. But sometimes, it's useful to try to find something worthwhile in all this. Because, we just spent a lot of time today. And for some of you, you're going to be like, what was the point of all that, right? But for me, as the person who likes learning and doing all this stuff, I think this stuff is fun, Like if I sat in this class today, I would be like, oh, let me go read about gamma decay and see if I can make any sense of it. And maybe that's just the difference between everybody's different and how they enjoy or how they want to learn and spend their free time. I don't know. But I think it was important for us, again, this is a physics class. It's important for us to do physics, at least in this case, an elementary level. And I don't mean elementary like school. I mean like, we can't go too deep into certain things, but when there are times where we can do a little bit of the physics and the math, we should. And I think this was a good place to do that. And then we'll do some examples. And then, hopefully you can sort of, be able to mimic them. It's not lost on me either that we jump from topic to topic in here. And sometimes as a learner, you feel like things are very scattered. But that's just one of the downsides of, teaching a class like this. So just to give you some perspective, we literally did the fundamentals of we did, what did we did like Newton's laws, and then we did, we do, I guess we do, how do we do? We did force first. So we went, what's a good way to say this without sounding silly? So we did like force and pressure first. And we did that in like one class. And then the next class, we talk about like work and energy and power. Well, we're not going into extreme detail, so it might seem like we're blowing you off. But if you look at force and pressure and work and energy, that's typically the whole freshman year of a physics major, right? You spend all that time. You don't even touch fluids likely until you're a junior or senior if you're studying these things in depth. And we're trying to give you a very small glimpse of some of these things, and we're hopeful that there's some context in which it could be useful for you. Obviously, some things could be more useful than others, like understanding gases and pressures is something that's more useful to you than I would imagine, at least. However, we can't spend a month doing that because A, at some point the math gets too difficult, and B, that's not the purpose of this course. So, we have to pick and choose that. So, I guess I'm going off on a tangent here. I apologize for that. But I do want you to keep that in mind when you're like, okay, because I like to look at like our lectures, especially now that they're all written down, and I say, what could have been good and bad in the last lecture? And I think about it from a student standpoint. We're talking about these electromagnetic waves, and I'm talking about sines, and then the next thing you know, we're talking about exponential, and it just seems like there's so many. As you, as the listener, the learner, you're probably like, it seems completely disconnected, but it's really not. And if you can make that connection, then you've actually learned some physics, even if you didn't. I'm not talking about working out scary calculations. I'm just saying, think about the amount of physics you learn if you just make the connection between, okay, we have charged particles. We know there's charged particles. If they accelerate, there's these things called electromagnetic waves. And then if heat is transferred using them, then we create this thing called radiation. So even if you can describe this process, not necessarily do calculations, if you describe that sort of hierarchy of what's happening, then you still learn something. You still have gotten something from it, even if you're completely lost by me doing solving equations. Anyhow, I think it's worth pointing out. I think that's fair. That's something that I should, remind you guys of if I want to be thorough on this. Okay, does anybody have a question? I'd like to do an example of a problem like this. All right, no one has a question. All right, so let's let's look at a sort of what we call, I've used this phrase a few times, like textbook problems. So let's suppose that A equals A naught equals e to the negative 1/100th t. Well, actually, let's not use A naught. Let's just start with a little more. Let's start with, how about 500? We'll start with numbers. So I'm not putting this in any context right now. I'm literally just giving you an equation, and I'm going to ask us to compute some things about this equation. So let's determine the value of A when t equals 0, let's say 5 in the 100. So I'm asking to compute 3 numbers. And the interesting thing about this is only one of these computations is going to be able to be done by hand. The other 2 are going to have to be done using a calculator. So when t is equal to 0, what is A? Well, A becomes 500 e to the 0. Now, one of the things about the 0 power, and you learned this, I always say you learned. That's probably unfair to say, because you're probably like, what do you know about what I learned? But one of the things that is taught in algebra class in high school is you learn about exponents and powers. And one of the properties of exponents is that any number raised to the power 0 is always 1. So this becomes 500 times 1, which is just 500. So if you look at this, this is why we call 500 the initial value, or the A naught. Why do we call it the initial value? Because when the clock hasn't started yet, at time 0, right when we're about to start observing, what do we have? What is our amount? And here it's 500. Okay, so what happens now when t is 5? When t is 5, A is equal to, once again, 500 e to the negative 100 times 5, which is 500 e to the negative 1/20th, because 5 goes into 100 20 times. And now at this point, there's not much that we can do unless we go to a calculator. So there's lots of calculators. I always recommend Desmos. You guys can use anything you want, handheld calculator. But we have to compute e to the negative 1/20th. And then we take that number and multiply it by 500. Well, what happened? I lost my, what am I sharing? What is happening? Yeah, okay. I lost my, in the heck? We're having technical difficulties. What happened to my, there it is. Okay. So if you compute this number, you get roughly 475.618, let's say. So does anybody have a question about this? Or maybe not sure how I got this number? If you do, please ask. All right, so, and then the last thing we'll do, we'll do it one more time. So when t is, what did I say, 100, I think. When t is 100, a is 500 times e to, this just becomes negative 1. And once again, you go to a calculator and you get, this is approximately 183.93972. So for this particular example, all we did was calculate 3 values. So this is literally just plugging numbers into a calculator. What's the half-life? Well, we can calculate that as well. Notice t, the half-life, t sub 1/2 is equal to, you'll recall it's log of 2 over k. What was our k here? So this might be a little confusing. The k is negative, excuse me, is 1 over 100. So from an arithmetic standpoint, this is 100 times log 2. And once again, if you want to know a value of this, at least an approximate value, you just go to a calculator. You get that this is approximately 69.315. So an interesting sort of game for you to play is to look at the 2 calculations above. You look at t, when I want to know what happens when time is 100, whatever that is, days, seconds, whatever. Notice that when after 100 units of time, I'm down to 183. Well, that's below half of it. Half of it would be 250. And so our calculations are in agreement with each other. So that's always good. Does anybody have a question or a comment? No questions. It's the quietest day. No questions. You guys didn't even, no one's even asked anything. You guys should be asking about how the tests will be, or you can be yelling about grades, and you can, all these things you can be complaining about or asking, and it's just silence. Silence. By the way, I should mention there is going to be one more homework as well. You're like, well, that's not fair. Well, it'll be an easy one, I promise. All right, so that's one type of problem that you should be sort of, I don't want to say capable, but you should be able to solve when it comes to this stuff. So let's do another problem. So, oh, by the way, let me show you something. I should have done this earlier because it's worth doing. Let's share good old Desmos with you. So hopefully you guys are seeing Desmos. I think you are. Yeah. So you can, if you want to graph this function, you can literally type it in verbatim. Now, notice I'm using different letters here. I'm not using T. Desmos likes Y's and X's. And then the next thing you'll notice is you don't see anything when you type the equations in. And that's because our window needs adjusted. So we need to sort of go tinker around. We know that at 0, it's 500. So maybe we should change our Y scale to put it at like 501 maybe. And then if we look at our X scale, so if we zoom out, we start zooming out, we're like, okay, that looks like what O'Grady babbles is an exponential curve. Sure. And if you look at the scale, and you can even look at the half-life, where's the half-life? Well, we want the half-life to be when it gets cut in half. So if I look at the height of 250, where do these things intersect? And you'll see they intersect at 69.315, which is pretty much what we calculated using our formula. And we can play with the scale even more so that you sort of see what's happening. Zoom out a little bit, sort of. So again, you see the half-life. Notice at 69.315, the amount left is 250, which is half. All right, so any questions about this example before we do? All right. Let's move on. How do I get this back? Come on. There we go. Sometimes the computer doesn't act the way. Here we go. So so given, let's do a different one now. Let's say A equals 100 e to the negative we'll use decimals now, 0.3 t. Determine the value of t that gives a equal to 14. Now, again, let me reiterate this. I could, you know, when we give you some other problems, we're going to put them in some context. But before you put any context in there that can be even more confusing, what we need to do is we need to make sure we can do the, in many cases, this is basic arithmetic. And in some cases, like this one, it's going to be a little bit of algebra. So, you know, hopefully when we put it into context, it's not so much different to get the solution than we have here. So how do we do this? So we have to translate this sort of English sentence into math. So we have to solve 14 equals 100 e to the negative 0.3 t. So if we want to solve that, the first thing we might note is if we divide both sides by 100, you get 14 over 100, which is the same as 7 over 50 equals e to the negative 0.3 t. And so when we're solving equations like this, one of the things I would caution against is going to a calculator too soon. So what I would encourage you to do is you do everything by hand to keep your numbers exact. And then once you're at the final step, then you can go to a calculator. So I don't know if that's clear, what I mean by that. But so what I'm saying is I wouldn't go to a calculator and compute 7 over 50 yet. I wouldn't approximate that yet. I'd leave it as 7 over 50. And what I, you know, to be more precise, what I mean by that is if I go to the next page, instead of writing 750 as a decimal, I'm going to write this as the log of 7 over 50 is equal to negative 0.3 t. And then that tells me if I divide both sides by negative 0.3 that t is the log of 7 over 50 divided by negative 0.3. So at this step, this is now when I'm going to go to a calculator. Now, I'm not saying it's wrong to go to a calculator the step before, but what I'm saying is if you want, one of the things we'd like to do is understand there's a difference between an exact answer and an approximated answer. And so what I have written right now, this is the exact value. And then when I go to a calculator, what I'm doing is I am approximating this value. So if I go to a calculator and compute this, and provided I do it correctly, I get the t is approximately 6.55371. So that number is 6.55371, approximately. Now, a thing that might be worth pointing out, because I've had this question before in the past, is you see that negative number there, and then but when I go plug it into a calculator, the number's positive, and you might think, well, what's happening? Well, if you go study the log function, this natural log, you'll note that the log of 7 over 50 is actually a negative number. So this answer does agree with what we did. You have a negative number divided by a negative 0.3, so you'd expect a positive number. So what I would encourage you to do is also do the following. So I would encourage that you should use the graph so to check your work and verify. So you want to make sure the picture agrees with your calculation. So let me explain through an example of exactly what I mean. So if I go back to Desmos, so let's start from scratch. I'm going to start with a brand new graph. So what was our expression? Our expression was something equal to 100 e raised to the negative 0.3 times the variable. And so if I move my scale around, I'll see that this is a curve that, if we've paid attention to some of the blabbering of Grady, looks exponential. And what does it, what happens? When is it, let's say, what did I say? Y equals 14. We wanted to know, when is it going to be at 14? And so if we draw that line and look at where the graphs intersect, you'll see that it's at 6.554 is what the computer's answer is. And what was our answer? So the computer gets 6.5, and that's what we got, 6.55371. So again, I'm using the computer to sort of investigate. I'm using it to validate my work. And you should use your resources if at all possible. All right, does anybody have a question, comment, concern about this? Going once, going twice. Okay, I guess unless you guys have a question, we should stop here. Does anybody have any comments, questions, concerns? Is everybody going to get an A on the final so we can, turn it in early? That way, if you don't have an A, I can yell on you and say, get an A, and then you resubmit it, everybody gets an A. That's the goal. I don't know. Then some of you are probably like, how do I even know what I have now? You didn't update the grades. All right, listen. Does anybody have any comments or questions at all? So I'm gonna again, I'm gonna send an email, or not an email, but an announcement. I figured I don't want to have. We can meet. I'll be available to meet Wednesday if you have any questions, particularly about the exam. But I don't know how you guys are probably a busy schedule, so I figure give you the class time Wednesday instead of meeting and giving you something new. Allowing you to use that time is at least something for the test. So if you want to meet, reach out to me. If you have any questions or concerns about your grades, please reach out to me. The goal is to help you guys all get a really nice grade and get a sheet of paper next year. So, all right. So, all right, I thank you guys for joining. If you have any questions, feel free to email me. And if I don't respond within an hour, send the email again.
Thank you.
Thank you, guys.
Thank you.
And, good luck on any crazy exams you might have. I'm assuming you will. So, all right, guys, take care, and I will talk to you soon.
Thanks.